Okay, we're back this time.
I'm going to do, going to allow the force to be 1. This is called the forced solution. The previous was free. When this was 0, it was free to do what it wanted to. I'm going to define the mass as being as 1, and then, like before, I solve the S equation, and then I also solve the differential equation. I'm not expecting you to solve the differential equation on an exam, but I am expecting the S equation. It looks ugly. Let's proceed on. Okay. So again, I'm going to choose some values. The first thing I'm going to do is I'm going to choose the frequency to be 2 pi radians. I'm going to choose no damping. Let's take a look at what the solution looks like. The solution is exactly what it was before if you look back. The point here is that the force has nothing to do with the transient response. The transient response only depends on what's in the S equation. There's no input term in the S equation at all. And so this is exactly the same transient solution. Is it stable? The answer is no. It is marginally stable, which means it will never get bigger or smaller, so it's marginally stable. How do you know? There is no real part in the solution. Does it want to oscillate? Yes, it does. It does want to oscillate. What's the frequency? The frequency of oscillation is 2 pi. You get that from the imaginary term. If you look at the solutions now, if you multiply this one out, it's a little hard to see, but if you multiply this one out, that times the 1 gives you an e to the negative 2 pi. This term times this term gives you a constant. And then this one times this guy gives you the e to the positive 2 it. So these two terms are in fact in there, in the decaying exponent, or in the exponent term. The 8 pi squared is part of the initial condition. This constant that you get from the middle term, this one right here, I'm multiplying the guy out by that, that's being caused by the force term. So this is the what happens at the end. So let's take a look at the plot. If you notice now that the average value is not 0 like it was before. That's being caused by the F over M term. This is the input. So basically you've pulled on it, and the spring comes over slightly, and it oscillates around that point. This guy here is going to be called the steady state. This is the steady state term. It never gets to the steady state term, mainly because it is marginally stable, which means it's not going to slow down, essentially. So let's see. Now let's put in some damping. Again, remember this is under damped. We'll take a look at what under damped means. You solve the S equation. Now you have a real part. So is it stable? Yes, because the real part is negative. What's the time constant? The time constant is, the quick way to do it is you change the plus minus sign of the real part and you invert it. So the time constant is 1 over pi. How long does it take until it gets to the steady state? That would be 4 time constants, and that would be 4 over pi. This is the same thing that we had before, if you remember, which is about 4/3 approximately. Approximately 4/3, about 1.3, which is right about 1, 2, 3, right about here. So from here over is the steady state, and here back is what we would call the transient. So let's see, what else could I ask you? Does it want to oscillate? Yes. How do you know? Because it has an imaginary term. What's the frequency of oscillation? The frequency of oscillation is equal to square root of 3 times pi. Which you can, and these would be radians per second, as usual. It's hard, again, to visualize the frequency because you don't get too many humps before it has decayed away. let's see, what else do I need to point out? The steady state value is right here. So, and you probably could expect that if you had a mass and a spring and a little bit of a damper here. And you either pull or push or whatever on this thing with a constant of 1. When it settles down, the spring is going to be compressed a little bit, and so the mass is going to move over slightly. So that would be the steady state value, and that's what this is right here. This is steady state value. Because you're pushing on it, you're compressing the spring at steady state. So that's the steady state value. I'll show you later how to find the steady state values of this. Okay, here's the same thing. This time it is overdamped, right? Say it is greater than 1. And here's the solutions. Right? So it's a negative 4 pi. And notice that this is a real number. So does it want to oscillate? No, it does not want to oscillate because there is no imaginary term. What's the time constant? This is the same problem I had before. I don't have the numbers. You're going to get two negative numbers when you punch in what 4 pi minus 2 square root of 3 pi is. I think one was a negative 23 or something. I think I made a mistake on that, but one was like a negative 23, the S roots, and the other one was like a negative 1.6 if I did the calculations right. Again, the time constants you have, looks like you got two of them. One is 1 over 23, or it's 1 over 1.6. This one is the bigger one. You choose the bigger one and give me that. Here is the solutions. They look really pretty ugly, but if you notice, they've got these decaying exponents. If you multiply this through the term there by these terms right here, you'll end up with some constants. Okay, so if you dig through here and pull it out, you'll end up with some constants. The graph is probably the easiest way to see it. You can see that what's happening is this thing's beginning to kind of level off. If you just keep going, it'll just kind of look like it becomes flat. Okay, so at what time does it get to the steady state? Well, that would be 4 time constants. 4 time constants is about 4 over 1.6. 1.6, and so what is that? 2, somewhere between 2 and I don't know, somewhere around over here, maybe, I guess. 4 over, yeah, somewhere over here. So right over here is probably right about where the the steady state occurs. So this would be the steady state. I'm just trying to do this in my head, and then less than that is going to be the transient solution. And you see it doesn't have any desire to oscillate. The steady state value becomes a constant that you'd expect. If you had this spring and a damper, and you push on it with a constant force of 1, it's going to move over, and this would be your steady state value, just like it's the steady state value here. Right? And like I said, I'll show you how to find those from the S equations later. Okay, so now what's going to happen is I'm going to shake it. So now that instead of having a constant force, what I'm going to do is I'm going to have a sinusoidal force, something like this. So it shakes it back and forth, similar to your ceiling fan thing. And so here's the solution to the S equation. Here's the differential equation solution. Here's the other differential equation solution. They look different, but I'm going to try to show you that they're the same. So again, I'm going to take the same thing, this time no damping, and we'll have an omega of 2 pi. We solve the S equation. This is the S equation. Notice again that the S equation solution is exactly the same as it was when you had no forcing term. The reason is because the S equation solution is telling you what's happening at the characteristic of the system has nothing to do with the input. And so it doesn't matter what your input is, the S equation will have the same solution. So is it stable? No, it's marginally stable. What's the time constant? There isn't one. It never gets there. So does it want to oscillate? Yes, it desires to oscillate. What is its natural oscillation period? 2 pi. So the natural, what it wants to do is 2 pi radians per second. That's what it wants to do. What am I doing to it? I am shaking it at a different frequency. I'm shaking it at pi over 2. It wants to oscillate at 2 pi. Okay, so what's going to happen is you've got this weird, basically two frequencies that's happening here. So you can see it right here. Right, there's a basic, if you count humps, 1 hump, 2 humps, 3 humps that occur over time at a lower frequency, and then here is these inner humps, the smaller pieces that are happening in here. So there's basically at least 2 frequencies that are making this up. What are the 2 frequencies that are making it up? One is the natural, and the other one is the forcing. So it's a little hard to see what's happening when there's no damping, but the point is that there will be 2 frequencies in there. One is the natural, and one is the forcing. So what I've done in this second graph is I've drawn the output along with the input. So here is the input shaking force. It's a sinusoidal force. And you can see that these big humps right here are occurring at the time that the force is occurring. So every time you have a hump on the input force, in this case you got 1, 2, 3 input force humps, you're going to get an output, a major, primary, whatever you want to call it, output hump. Right? So basically these lower frequency things are occurring because of the forcing term. Okay, let's do it again. This time we'll put in same natural frequency. This time we'll put in some under damping, and the forcing frequency is the same as before. So we're forcing it at a frequency that's lower than what it naturally wants to do. And so let's see what happens. So here's this thing that you saw before, right? And if you look at the S solutions, okay, now you have a real part and you have an imaginary part there, plus and minus the imaginary part. So does it want to oscillate? Yeah, it has a desire. It desires to oscillate because of the imaginary term. What's the time constant? The time constant in this case is you flip the plus minus sign, so it's plus, and you invert the real part. So this would be 10 over pi, which is about approximately 3.3 seconds. When does it get to steady state? 4 time constants. That would be about 12, 13 seconds or so. Okay, so let's see what's happening. At the beginning, you can see that it has the hint of the 2 frequencies, the natural and the forcing. By this second hump, it's beginning to even out, or whatever you want to call it, but it's still a little bit there. You can still see a little bit of it. And then by this third hump, it's pretty much gone. You can't really see. The steady state is really going to occur after 13 seconds. So about over here, this is going to be your steady state. I should have plotted it a little longer. It's a little bent here still. It's kind of a weird shape. But eventually this thing is going to become just a pure sine wave like this. So what is this frequency that's occurring? Well, it's easier if you look at the input, which is this red one here, along with the output. And you can see that what's happening is the output is shaking at the same frequency that the input is shaking. And so what you should take away from this is that the frequency that whether even if it doesn't want to oscillate, it will oscillate if you shake it. If you force it to, it will do it. And it will oscillate at the frequency that you force it to. May not be what it wants to do, but that's what it will do. It will always oscillate at the frequency that you force it to oscillate with. So that's the takeaway for this. And let's see, I have another one. This time, it's still under damped. let's see, we're changing the input frequency, the shaking frequency. Now it's half of what we had before. The time constant is exactly what it was before, because the damping is the same. So if you notice, 2 pi and 1/20. So the transient has absolutely nothing to do with the force. This is the only thing that's different right here. And so the transient solution is exactly what it was before. The settling time is about 13 seconds, so steady state's going to be over here. It's a little harder to see the thing at steady state, but the steady state's over here. And let's see. At the beginning, you can see, it's a little difficult to see, but at the very beginning, you can see that these are kind of bent, not quite the same nice smooth shape as when you get out here close to the steady state. So it does, in fact, have a transient. It's just a little hard to see. It's probably easier if you look at the kind of the peaks, maybe. You can see how it's kind of going up a little bit over here. That is the transient. It's just hard to see. And again, the output right here, the blue, and compare it to this guy, you can see that the blue is shaking at the frequency that you're forcing it to. That was the point I was making before. Hopefully it's pretty obvious. Now what happens is I have some damping, same as before, same natural. This time I'm going to shake it at the natural. So now I'm going to force it to do what it wants to do anyway. And if you notice what happens, transients stay the same as it has always been. No big deal there. Here's the solutions. If you look at the 13 seconds, did I have that plotted up? No. Okay, so this is a little bit better. 13 seconds right about here. From here out is the steady state. You can see that it's pretty much uniform out here. The other thing is, notice that the steady state is not constant, which doesn't have to be. So if you're shaking it, the steady state is not going to be constant. It's going to follow the input. Obviously this is the transient. It's building up back over here until it hits the steady state. Let's see, is it stable? Yes. How do you know? You look at the S equation. What's the natural frequency? This is the natural frequency. This is what it wants to do. I happen to be shaking it at that frequency, and that's why it builds up to this point. If you want to put energy into a system, if you want energy in, you shake it at its natural, if it has one. So that's kind of a takeaway for this. And then here is a plot of the input versus the output. And so this is still part of the transient here, so it's building up. But you can still see it even at the transient, that every time you have a red input, you have a blue output. Red input, blue output. The amplitude of the output would be from here, from the center point up. This is the amplitude. Oftentimes people will give you the peak to peak because it's easier to measure graphically. You just draw a line, and then measure the distance between them, rather than trying to find the middle point. So that's the amplitude. The other thing to notice is that there's something called phase, and that'd be this guy right here. So if you notice, the output is different from the input. The input hits its peak at a different time than the output, and so that would be called the phase shift, and you want to measure that in angle. So phase shift is measured in the amount of angle between the input and the output. That's the phase shift. Okay, so here we go. Now what we're going to do, we have the same system characteristics, same natural frequency, and the same damping. It's under damped. This time I'm going to force it faster than the natural frequency. And is it stable? Yes. What's the natural frequency? Same as it always was. That didn't change. It has nothing to do with the input. And so here's what's happening. The steady state's going to occur out here. Here's your steady state at about 13 seconds, and we're running here. So that'll be your steady state. It's oscillating much faster than it used to be. If you look back over here, you can clearly see these two frequencies. There's the forcing frequency, which is fast, and then there's the natural frequency, which is a lot slower. And that's in there, and you can see how it's decaying away. Okay, so zoom in on the initial. This is the transient portion, but if you notice here, it's still building up. See, because how it's one's high, one's low, one's high, one's low, until eventually it gets to steady state and settles down. So it's a little harder to see, but if you notice though, there's still a phase shift between the input and the output, and for each input peak, there's an output peak. So that means that the output is shaking at the frequency you're forcing it to do. And then there's also this YouTube video if you want to take a look at that. So what is the takeaway? The output frequency will be equal to the forcing frequency. The transients, the time constants, etc., have nothing to do with the input. So that's it, and then we're going to do some more problems